Now before we move on, we need to go back to the visible light. Over there to the right hand side of this picture in your notes, you have our friend Roy G. Biv. And I know you know by now that that stands for the colors of the rainbow. Red, orange, yellow, green, followed by blue, indigo and violet. That's a rainbow song for you. I have kids, I watch Cat in the Hat. Shut up. So those are the colors of the rainbow. Write those in. But more importantly, you see in that box beside there that the colors of the rainbow, as indicated in this picture, go from low energy to high energy, from the red end to the purple end. So the red-orange end is what we refer to as the low energy end. The blue-violet end is the high energy end. In fact, as I said before, the indigo is really nothing different than blue. We put indigo in there just to make a nice word that's easier to pronounce. But we typically call this the blue-violet end, and this is the red-orange end. This is the entire electromagnetic spectrum broken up in a different way, and you need to be able to learn this spectrum. The first thing I want to say is what's written up here. Not all light is visible. The light that we typically refer to is this part that's right here in the middle. But this part, this light, is no different than anything else we've seen. It's all an electromagnetic wave that looks like these waves that I showed you here. Still looks like these waves. So there's no reason to refer to visible light or any other light. A lot of times the word light we use to refer to the entire spectrum. So if I say the word light, whatever I can say about light is also true of a radio wave or a microwave or infrared radiation or everything else. So to learn the regions of the spectrum, there's a really fun word you can learn that's pronounced Rumivixg. Or if you don't like sounding weird, you can learn this little sentence: red Martians invaded Venus using X-ray guns. So write that in your notes, and underneath the blanks where you wrote those, you need to write the regions that those words refer to. Know that this phrase is in order from low frequency to high frequency. So red stands for radio waves. Again, that was the lowest energy radiation we have. Microwaves are kind of in between infrared and radio waves. Microwaves are used by cell phones. That's low energy radiation, not a problem. Infrared radiation is I. V is actually visible light, and it's all of this that's blown up here, but remember, visible light is the smallest portion of the spectrum that we recognize. Ultraviolet is the U, X-ray is obviously X-rays, and the G stands for gamma rays. You need to know the order of the regions of the spectrum and which end is high energy, low energy, high frequency, low frequency rather, etc. Now, there's been a debate going on for a long time about the behavior of light and exactly what light is, and it's not an easy question to answer. But about 200 years ago, there was a big debate going on, and some scientists said that light was a wave, some guys said it was a particle. Turns out actually it behaves in both ways. It's both a wave and a particle, and depending on how we look at light and what it does, sometimes it behaves like a wave, sometimes it behaves like a particle. So let's look at the wave behaviors first. There are 5 wave behaviors of light we're going to talk about. That's reflection, refraction, diffraction, interference, and polarization. Say that 5 times fast. We've already talked about 4 of these in previous videos. The 5th one, polarization, we'll do today as well. But all of these are non-specific wave behaviors. All waves can do this. And so these things that light does proves that light, at least in part, behaves like a wave. So first, reflection. Reflection is easy. It's when light bounces off of stuff. It bounces off of mirrors, off of glass, off of water. As a matter of fact, light reflects off of every single surface. That's the reason why you can see anything, is because light hits an object and it reflects off of that object back into your eyes, and specifically reflects only certain wavelengths of light. For that reason, that's the reason why you can see different colors, is because only a certain frequency of light is reflected back to your eyes from different objects and different materials. The law of reflection states that what's theta r, theta I, this says in words that the angle of incidence, I stands for incidence, equals the angle of reflection, R stands for reflection. This is a complicated way of saying basically that however the light comes in, it's going to come out the same way. A tennis ball does this, a baseball does this. We know that if I want to bounce a tennis ball this way, I can't throw it straight down because it's going to come out the same way that it came in. That's obvious to us. What may not be so obvious is that how we measure these angles is measured in reference to a line that is perpendicular to the surface. Very important that you know that. The line is called the normal. The word normal means perpendicular. So let's look at the picture of the law of reflection here. This picture is in your notes. You have this line drawn and this line drawn. This line is the surface and this line is the normal. You might want to even draw a little box here to tell yourself that these two are perpendicular to each other. Then we have the incident ray of light coming into the surface, the reflected ray of light coming out. The normal line, since it is perpendicular to the surface, actually serves to bisect the angle made between the incident ray and the reflected ray. And the word bisect, hopefully you remember, means that it cuts the angle in half. And that is the reason why the angle of incidence is equal to the angle of reflection. As we said before, we always measure those angles between the ray and the normal. Always measured between the ray and the normal. We do not measure the angle between the ray and the surface, simply by convention. These two angles still would be equal to each other if we did measure them, but we're not going to measure them simply because we need to get in the habit of not doing that when we get to refraction later. So the angles are measured between the ray and the normal, and those two angles are equal with reflection. Next is the law of refraction. We've talked about refraction and we'll talk about it more so in detail later. But refraction happens when light bends. Light bends when it changes speed. The only way to change the speed of a wave is to change the medium. Therefore, refraction is the bending of light due to a change in medium that the light is traveling through. So this is when light travels from air into water or from air into glass. When it does that, it bends. Remember, these are all wave behaviors. Waves do these things. Single particles do not. If it was a particle, such as a bullet, bullets will go into water and keep traveling in a straight line into the water. Particles do not bend when they enter into a new medium. Waves do. This is the pencil looking bent in the cup of water. This is looking at a crawfish underneath the water, and it looks like it's not where it's at. Your eye would be here looking at the crawfish, and your eye traces the line straight back, and it looks like the crawfish is here when it's actually over here. This is due to refraction. All right, and these funny pictures that we did in class, we have one of these water prisms, and you can make yourself look pretty funny with these pictures. This is just due to refraction. The next one is diffraction. Diffraction is also when light bends, and in this case, light spreads out because it has a lot of different wavelengths, and when light bends, each wavelength will bend a slightly different angle. Therefore, the colors of light spread out. But in diffraction, we're actually not changing the medium. We're sending light through something like a diffraction grating, which you can imagine is kind of like prison bars. And what happens is light comes through here, and as it moves past the corner of each barrier, it spreads out into its individual colors. That's called diffraction. This is what you see with a hologram on a credit card, the colors you see on a CD. The rainbow effect that you get is due to diffraction, and sometimes rainbowing is due to refraction. The actual rainbow that you see in a rainstorm is due to reflection and refraction because it's going through a different medium. Interference is the next wave behavior. We talked about interference with sound, and I showed you that on a video. We can get constructive or destructive interference. Interference, remember, is when waves meet together. If they constructively interfere with each other, that means they meet in phase, and the result is a high amplitude wave. If they destructively interfere with each other, that means they meet out of phase, and the result is a low amplitude wave. So these are waves meeting in phase, and they get high amplitude, higher amplitude. Out of phase, you get low amplitude or nothing. So with sound, we got that loud, soft beat pattern. Well, we get the same type of thing with light, except it's light, dark instead of loud, soft, because amplitude with sound results in volume. Amplitude with light results in brightness, right? And there's a really good video that explains Young's double slit experiment that you need to go and watch right now. I'm going to end the video and go onto the website and look at the very next video. It's Veritasium's explanations of Young's double slit experiment. It's very important that you understand that experiment, and then I'll come back and explain the experiment. Actually, let's do this. Why don't you just click on this link right here in the video, and you can go watch the video now. All right, hopefully you understood that video, and I want to rehash exactly what he was talking about. This is Young's double slit experiment, and actually there are two wave behaviors that are being shown with this experiment. The first one is actually diffraction, and what happens, remember, is we have these two slits here. If light is a particle and it passes through those two slits, such as spray paint, you would get a pattern of light on the other side that looks exactly the same as the two slits, almost like a stencil. Spray paint would go through and it would paste onto the paper exactly the same way. It wouldn't move. It would just go straight past those two. But if we look at these two from the top down and draw it like this, here are our two slits. The light waves are coming through into these two slits, and instead of moving straight in a straight line past them, the first thing that happens is diffraction. Diffraction is when light spreads out past the corner of a barrier, and so we get this type of pattern after the light goes past those two slits. Okay, so the first thing that happens is diffraction, and diffraction makes the second pattern possible, and that is interference. So Young's double slit experiment actually shows two wave behaviors. Diffraction, so first of all, if it's not a wave, the light doesn't refract and it goes straight through, which we don't observe. And since it is a wave, now the waves can interfere with each other, such as what he said, and we get the light dark pattern that we see here, that we saw against the bottom of the box. You can do this experiment at home. We get a pattern that looks like these pictures that I'll show you here. So here's the experiment, light coming through, it diffracts, then we get the double slit, it diffracts again. This is the area of interference where the two waves are meeting each other. Since they are interfering each other, we get the high amplitude, low amplitude, high amplitude, low amplitude pattern resulting from constructive and destructive interference. Therefore, we get this. If light is just a particle, it does this. Since we observe the wave part, the wave behavior, then this proves that light is in part a wave. Here's another example of it. You can do this with a laser. We get green, dark, light, dark patterns, the min, the max, the min, the max. And here's an example of the water that he showed there on the pond. If you look carefully, these waves are interacting with each other. There's a line of constructive interference going through here. There's another line of constructive interference going through here. It's hard to just trace this. Constructive interference here. And in between those, we get destructive interference, right? Destructive, 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 to the point where when we come all the way out here, if this is the bottom of the box, we had a constructive area here, constructive area here, constructive, constructive, constructive. So all those circles will be bright, and in between would be dark, dark, destructive, destructive interference. That's the result of interference with light. The last wave behavior we'll talk about is polarization. Polarization happens because, or it happens that when light can vibrate in one plane only. But the problem is light from the sun and most other light is actually non-polarized, which means it actually vibrates in a whole bunch of different planes. What I mean by that is, remember we had one wave coming this way, the other wave going this way. This is going up and down, this one's going side to side. What happens if we look at this one from straight on, this wave looks like this. And actually, let's scrap this and let's consider it. Let's just consider one of these waves, right? Let's just consider one of them that it does like this. So if you look at this wave straight on, it's the particles are vibrating up and down. Well, non-polarized light, you actually get waves that are vibrating in all different directions, and some of them are vibrating like this, some of them are vibrating like this, and so you get all sort of directions to this wave as it goes in. And what a polarization filter can do is, again, you can imagine it kind of like prison bars, and when all of these sound waves go through here, it's not hard to see that the only ones that get through are the ones that are parallel to the filter. So this one doesn't work, this one doesn't work, this one doesn't work. The only one that goes through in this one, that's the way to get light through on the other side that is filtered, that is vibrating in only one plane. So this is the polarizing filter that lets only one vibration through and blocks all others. Again, here's the sunlight, here's the filter. Only the vertically vibrating light can get through. And I'm going to show you a demonstration in just a minute that proves this part of the polarization. Actually, not just a minute, there'll be a second video about the polarization demonstration.